I'm the past executive director of the Regional Science Consortium, but I have to pinch myself to make sure I'm still here, not past. It's my pleasure to welcome you to the second session of the 14th year of the Regional Science Consortium's Research Symposium. We've been doing this, it's been growing every year, and under Jeanette's leadership, it's expanding very nicely. So I'm pleased to welcome you here. And our next set of speakers are all from Mercyhurst University, and they're all in the area of forensic science. So it's my pleasure to introduce, first of all, Randi Depp. Randi, Dr. Randi? Master.
I'm a master's student.
Okay. Randi Depp is going to talk to us about bacterial communities of human remains and adjacent soils in forensic settings, applications for postmortem interval estimation. Randi.
Hi everyone, thank you for coming today. So I'm a second-year master's student in the Department of Applied Forensic Sciences. This is my thesis project. It is currently underway, and I am doing my research here at the Tom Ridge Center. So I'm just going to give you some background information and then talk about my methods and what I hope to achieve here with my project. So the postmortem interval is the time since death. So for those of you not in forensics, this is essentially the time since the person expired to the time of discovery. And this is really important information for police because that helps to narrow down the potential identity of the decedent, and it also helps to establish a timeline of events surrounding the death. So if the person has been dead for 2 weeks and they have a missing person who has been missing for over 2 months, it's unlikely that that is the person. So this is important for law enforcement to utilize. Now, PMI estimation is very challenging, and it's because there's a lot of variables that are involved in the decomposition of human tissues. It's a very complex biochemical process. It has a lot of different stages. The first one is autolysis, which is cellular death. It's followed by putrefaction. So this is the enzymatic breakdown of tissues. And this is both anaerobic and aerobic processes. And then it's followed by decay, which has many different stages. And it will depend a lot on the environment and the weather to indicate how fast the stages will go and what the outcome of those stages will be. So historically, PMI estimation is based on gross qualitative methods that require a lot of experience. And it looks a lot at soft tissue. So the qualitative stages might be something like fresh, bloat, active decay, advanced decay, dry, and skeletonization. And that sounds great, but experts in the field don't agree on what these stages are, how many stages they are, what they're called, and what actual attributes identify each stage. So there's no agreement on what to call these stages or what the different time markers are. And also, these all vary on climate, the decedent's profile, and the observer's preferred classifications. So there's not really a good way to characterize the postmortem interval. So a lot of times entomology is used. And so entomology, they look at the life cycle of the insects to determine how long it has been since the body was placed there. There's also been quantitative methods that have been tested. Unfortunately, a lot of them are fairly unreliable. There are accumulated degree days, so you're looking at the temperature, the average temperature on a daily basis to see how much tissue would have decomposed, regression formulae, and also biochemical markers, both in the tissues and in the soil. It's especially difficult to estimate PMI in forensic anthropology, which is what we do at Mercyhurst. The existing methods rely on those soft tissues to indicate the postmortem interval. And this is usually 6 months or less, where the soft tissue is remaining and identifiable. But the problem is most of our cases are 6 months or more. So what do we do? How do we assess that? So a lot of times we have to look at context and associated materials that are at the scene to assess PMI. And that PMI is usually presented in very broad ranges. So we're giving the police months, even years, or decades. So it's not uncommon to say, this person has been deceased for 2 to 5 years. That's a lot of missing people, potentially. So that's a problem. So recent taphonomic studies have demonstrated the use of bacterial community succession in order to estimate PMI. And they're looking at the bacterial communities of both the human remains and also soils. Because as the body is in contact with those soils, there's an interplay there with the microbiomes. Most data so far, however, has been collected at 6 months or less, much like the previous qualitative studies. And very few use human remains, which doesn't seem to be a problem. We use animal proxies a lot. However, animal proxies do not have the same microbiome as humans. So are they the same groups? We don't really know any of that. Also, there's no published data on forensic cases specifically, data collected at the crime scene. And currently, most of these studies, they use metagenomics, so they're looking at bacterial RNA to sequence that and identify specific strains or species. However, all of that data kind of boils down to the phylum and family level is really showing the most patterns right now. So do we even really need to spend the money on RNA sequencing? Because it's really expensive. So my goals for this project, I would like to contribute to the current body of knowledge regarding bacterial succession. So I'm going to be using forensic cases that we use at Mercyhurst University, using that expanded PMI range that we encounter in forensic anthropology, and also, like I said, using actual human remains. Second, my goal is to determine if bacterial succession is correlated with PMI in forensic anthropological settings. And third, I'm going to be testing sampling protocols and best practice guidelines. Like I said, no one has sampled stuff from a crime scene before in this manner, so I'm going to see if it's even feasible. I'm also doing a culture-based approach, trying to see if it is more feasible to do culturing instead of the RNA sequencing, and if we can get a pretty rapid response, a pretty rapid result just by doing a few simple cultures. So I'm going to see if those methods even work. So specifically, I'm going to look into what bacteria are present on those decomposing human remains. So I'll look at whether or not the groups of bacteria are correlated with the PMI, and also if there's any differences between my two sample groups. Next, I'm going to look at what bacteria are present in the soil adjacent to the decomposing remains. So same thing, I will be looking at whether or not the communities of bacteria correlate with the PMI, and also if there's any change related to the proximity to the human remains, to see if maybe there is some sort of progression as you get further away from the body. Then finally, what's the best way to collect and to culture the soil bacteria from forensic scenes? I say soil bacteria specifically because it's very difficult to grow soil bacteria in the lab, so I have a few methods that I'm going to test out in the laboratory. Specifically, I'm looking at the pH. We have a long transport time between our crime scene and our lab, so it could be upwards of 5 to 7 hours of driving, and depending on when I collect on the scene and how long it is before we actually leave the scene, the samples could be sitting in the cooler for 10 plus hours. Is that going to affect the quality? Is that going to affect the feasibility of this for law enforcement to use? So my sample, I have two groups. The first one is going to be 10 to 20 plus cases from the Erie County Coroner's Office. So those will likely be mostly flushed cases. Group 2 is going to be about 10 plus cases from Mercyhurst Forensic Recovery Team, and those are most likely going to be skeletonized. That's what we usually recover. So I'll be taking two different types of samples. I'll be taking swabs of human remains at two different sites on the body. So if it is going to be a fully fleshed body, I'm going to focus around the oral cavity and around the anus. If it's skeletonized, the corresponding skeletal material underneath. So the maxilla, so right here, or the ischium, which is where you sit. And those are usually the bones that are recovered most often at our cases, so that's why I chose those locations. And then two soil sites will be sampled at each scene. The first one's going to be the center of the remains, so right directly under the body. The remains are scattered throughout the woods. It'll be the center of the scatter. And then 5 meters from there will be the second location. And then I will be making a soil-specific media from each scene. So I'll take a 5th sample from the scene to create a soil-specific media to see if I can encourage those bacteria to grow in the laboratory. So I'm going to swab the human remains with sterile swabs. And those soil samples are going to be collected with a sterilized core and then put into sterile whirl-packed bags. And I'll be testing the pH on the scene of each sample location. I'm also going to look at the temperature just to see what the temperature of those sites are, if there's any sort of insect activity or bacterial activity creating some sort of heat signature. I'm going to look at that. And then all of the scene data will be collected for the Mercyhurst cases. So this is going to include the setting, the weather, vegetation, stages of decomposition, animal activity, sun exposure, those sorts of things. See if there's some sort of interplay with those details as well. And then the samples will be transported here and stored up to 24 hours until analysis. And then I will begin my laboratory analysis. So soil samples, I'm going to measure the pH again in the laboratory to see if there's any sort of significant change. And then I will be isolating the bacteria and culturing them directly onto Petri dishes. Swab samples, I'm transporting them in a buffer solution, so I'll be streaking that directly onto the plates and culturing from there. Here's a list of my culture materials, or media. So I'm using 4 different standard medias, and then I'm going to create that 5th soil sample, soil-specific media to see if I can get that soil bacteria to grow. And then I will autoclave those plates and then incubate them at 35 degrees Celsius for 48 hours. I will then follow up with bacterial identification, so the typical visual methods, looking at the colony size and shape, margins, opacity, texture, that sort of thing. And then maximum growth using colony counting. I'll run some presumptive ID tests like gram stain, catalase, and oxidase tests, and then other methods as needed as I go. And then finally, I'm going to compile all my data and use regression analyses to determine if there's any significant relationships between the scene data, those bacterial communities I've identified, and the postmortem interval that we've determined from the scene. So currently, I'm going to begin sampling in the next coming days and weeks, and I will proceed through January and February of next year, and analyze my data February and March. We'll be preparing my presentation paper in March to May, and then hopefully defending my thesis in May of 2019. So that is the goal, fingers crossed. So yeah, that is my project. Anyone have any questions?
Yes. What were the reasons that they chose the oral and the anal cavities? Like, I'm expecting maybe a mix of differences because depending on the nature of the crime, there would be possibly like no load in the oral cavity, whereas there might be the anal.
Yeah. So the main choice for the locations of the swabs was the what I will recover on the at the Mercyhurst cases because a lot of times scavengers take away remains, and so usually we find the skull and the os coxa are the more common, I guess, bones to recover, and so I wanted to be able to correlate those remains with the remains that I'm going to be sampling at the coroner's office, which are generally fully fleshed. So I wanted to make sure they were about the same region. If I don't have those on scene, I'm going to have to assess and take that at a case-by-case basis because we encounter a lot of weird things. So it's really hard to predict what will be available. So I'm trying to generalize with that.
Do you anticipate a difference if you collect your sample in different weather conditions?
Yes, I think that's going to be a challenge, especially if it's been very rainy and wet lately. So I think if I went and sampled something this weekend, I'm going to get a completely different sample than if I had sampled, a month ago, and if it was the same scene. So I think weather is going to play a huge role in that, especially as we come into winter and there's potential for snow. I think that might alter it as well. Yeah.
Other questions? Thank you.
Okay.
We have a little time, so I'll talk slowly. And I'd like to introduce Rhiann Dunn, Masters of Science, Mercyhurst University. Estimation of American black and white ancestry from measurements of the vertebrae and sacrum. Rhiann.
Hello everybody, my name is Rhiann Dunn and I'm an instructor at Mercyhurst University. My presentation today is going to be on my master's thesis that I completed while a student at Mercyhurst University. Thank you for all coming. So first off, for my master's thesis, I did a validation study, which is actually pretty common, especially in forensic science disciplines, just because it's something that's feasible to do in 2 years. But before I kind of get into what I did about my project, I'd like to first talk about what a validation study is. So a validation study is when a method is tested with the same techniques under similar circumstances to note any discrepancies. So basically, if an original study is done, you're retesting that study to see if it's still going to work, whether you have a different sample or something like that. This is important because while you're testing its validation, you're also testing its reliability. If you're able to actually complete your validation study, you've proven that you can actually do it a second time. So you're able to test both factors through this. And it also is really important just because it allows us to understand whether or not a method is actually whether we should be using it for our field, whether it's valid at all, or if it was just valid in the first original study. It's especially important in forensic anthropology because we had a court ruling in 1993. It was Daubert versus Mao Pharmaceuticals. And basically, at the end of this ruling, they decided that all validation studies and all studies used in forensic science should be reliable, valid, and have known error rates. So this is extremely important because if we're going to be going to court for forensic cases, all of our results should have some scientific backing. But a problem is a lot of validation studies thus far only really look to see, hey, did it work a second time? You know, they're not really looking to see how it's working. So it becomes sort of this black box model. You're basically putting data into a box where you can't see what's happening, and it just chucks something out. And you just look at your results and say, yay, it worked, or yay, it didn't. Or nay, it didn't, I guess. So there needs to be a bigger focus on why these methods are actually working, especially if it's not discussed in the original study. So forensic anthropology, as that's my discipline at Mercyhurst University, is the application of principles utilized in the anthropological subfields of archaeology and physical anthropology to forensic investigations. So if any of you have seen the show Bones, we often get skeletons. We analyze the skeletons so that we can help police in their investigations. So to do this, part of the time we create a biological profile. So we will estimate age, sex, ancestry, and stature. This will allow us to come up with some known, basically factors of identity, so they can compare it to a missing persons list or any other individuals police might believe this individual is. So we're just sort of helping assist with that identification in part. For my thesis, I focused on ancestry estimation. Ancestry is the phenotypic variation that can be reflected in the skeleton, meaning that us as forensic anthropologists can see this variation and therefore estimate something based on it. So in this case, we can get an idea of what that individual's ancestry was. Generally, it's a proxy of geographic region, the three main being European, African, and Asian. So these are very general categories, but it basically is something to give us a direction to go. Why do we estimate ancestry? It's something that's included on the missing persons list. It's something that's going to be on your driver's license, so it's another factor that police will use to help identify individuals. In addition, other aspects of the biological profile, such as stature estimation, depend on ancestry estimation, because we use different methods depending on an individual's ancestry. But there are some problems in ancestry estimation. Most methods thus far focus on the skull, particularly in the mid-facial region, which would be like right here, so right around here, which makes sense because a lot of times when we look at individuals, everyone is very different often in their face. So oftentimes we can estimate based on those phenotypic variations. These traits in this mid-facial region are called macromorphoscopic traits, and there's been a lot of study in this area. So the skull is good. But a skull is not always guaranteed in forensic anthropology. I've been on cases where we've recovered a humerus. You never know. Just like Randi said in our last presentation, we always have to be looking for every possibility. But there's been little research done on the postcrania, the postcrania being all elements below the skull, so neck down. So is the postcrania is it even useful for ancestry estimation at all? I don't know that we know this as a subfield or a discipline yet. A lot of methods are used for ancestry estimation. The most popular method for postcranial ancestry estimation is a program called 4DISC, where you take measurements of the body, such as length of the bones, and put it into a computer system where linear discriminant function analysis will group an individual based on its similarities to other groups. So, for example, if you put measurements in of an individual, if it's most likely like one ancestry group, that will be your result. Other research has looked into curvature of the femur, basically the overall shape of your hip bones, and also your spinal column. But so far, we don't really see very good results. Then in 2017, Untitled released a method on vertebral and sacral measurements, basically all the bones that are in your spinal column, and got a 98% accuracy rate, which is basically 100%, right? That's pretty darn good, and caught my attention like this, as I was reading it at 11 o'clock at night. You know. What Untitled did was create 10 discriminant function equations, so 5 for male individuals and 5 for female individuals, based on different sections of the spinal column. So looked at the cervical vertebrae, those in your neck, the thoracic, your upper back, and your lumbar, your lower back. And was it trying to differentiate between South African, black, and white individuals. Basically, you put your measurements into an equation, you get a number. If it's above a sectioning point, that individual was of white ancestry, and if it was below this number, that individual was of black ancestry. So the reason I would like to use this as my focus for my master's thesis was for several reasons. It's a good option for a validation study because ancestry is the focus. If we're trying to, have great error rates and everything, good validation for these methods, technically in South Africa, we have individuals who identify in white as black, and we do in America as well. So if they're the same ancestry groups, we should be seeing the same results. If not, that maybe says something about what differences there are between the two populations and says something about ancestry estimation as a whole. Also, there's some holes in the original study. The author looked at t-tests, got significant results, but didn't explain what those results meant, just kind of went forward with the study and made equations. So I would like to validate Untilted's original study for ancestry estimation on an American population with 2 focus questions. Do the equations Untitled created classify American individuals with the same level of classification accuracy? Basically, are we going to get 98% accuracy here? And should these equations be sex-specific? If we're looking at ancestry, we just want to see this is just a different variable that doesn't really maybe necessarily interplay, so I just like to kind of investigate that to see whether or not it matters for this method. For this thesis, I went to the Hammond-Todd collection at the Cleveland Museum of Natural History. I chose this collection because it's an earliest 20th century collection, which is important because the original study was done in the Pretoria collection in South Africa. Potentially there might be exaggerated differences between white and black individuals due to the apartheid happening at the time of that collection was made. And in the earliest 20th century collection, we would see similar differences potentially if they exist because we still had segregation at that time. So this was to kind of decrease any error and try to replicate as much as I could the original study. I also had balanced samples, both in sex and ancestry, basically to see whether or not some differences are happening because of ancestry or just sex differences. So I had a total sample of 251 individuals. For my thesis, I tested 4 of the original 10 equations. I looked at both the male and female recognizable vertebrae equations and the male and female sacrum equations. Why? Because these equations are more applicable in a forensic context. If you're not sure what elements you're going to receive, you want to choose ones that you can recognize if you don't have the whole spinal column. If we're choosing the 4 recognizable vertebrae, we know that we can find them in any context. And the sacrum is obviously a different element, so we'd be able to identify that as well. For my thesis, I also created diagrams because the original author, who created descriptions of these measurements, didn't really go into too much detail, so in case I'm wrong in any sense of the word, maybe I interpret it incorrectly, I wanted anyone who's looking at my study in the future to know exactly what measurements I took. So I took 7 measurements of the vertebrae in different kind of capacities of that vertebral body. In addition, I took 6 sort of measurements of the sacrum, including sacral count, to get a similar shape difference. We're just trying to see overall, are we seeing differences in the shape of these elements? So, did it classify as well? Already you can see, not really. I'm not really getting those 98%. The highest I'm actually getting is about 76, 77. So no, it classified a lot lower than the original article, but technically it would be better than the prior. Like flipping a coin, if you only have 2 groups to choose from, about 50%, it's still kind of better, but that should be taken with a grain of salt. Additionally, male equations performed better, so this might say something about sex versus the female equations, but that's something I would like to investigate in the future. But this was just my first research question. Because Lundsterk in the original study said that there was no differences between the sexes. So I want to see would this hold true for an American population. And Lundsterk created and had accuracy rates for a combined equation for both the recognizable vertebrae and the sacrum, but failed to mention what equation he used. So I decided to test all equations to make up for this. So, male vertebrae equation performed the best sort of overall of the 4. But in general, they're all about the same as my previous results. But that begs the question, if I have 2 independent variables now, ancestry and sex, by combining them into the same equations, what's actually causing these classifications? So to test this, I did chi-square tests. Chi-square tests are important because they will test the classification of sex and ancestry independently, because they look at 1 variable at a time to detect whether or not a relationship exists based on that 1 variable. So I can look at first sex and then ancestry to see what's actually causing my results. So for a sex relationship, if ancestry classification does not depend on sex, both sexes should show the same level of accuracy, is my null hypothesis. So kind of looked at my observed versus my expected values, as we all do for chi-square tests, to get my results. And the female sacrum equation was significant, showing a slight sex ancestry, but all groups failed to reject the null hypothesis after Bonferroni's correction. In simple terms, there was no evidence of sex playing a role in ancestry classification. And if there was, potentially in that female sacrum equation, it's pretty slight. Then I have to test for ancestry relationship. So groups are actually classifying based on ancestry, would be my new null hypothesis. And I got all significant results. So all equations were classifying due to ancestry. So going back to my research questions, do the equations Lundsterk created classify American individuals with the same level of classification accuracy? No. But still sort of better than the prior, so somewhere to move forward with. Research question 2, should these questions be sex specific? No, because sex seems to play very little role, if any at all. So for my overall study goal of validating this method, for validity-wise, I was able to show that the original equations were classifying due to ancestry and not due to sex. So it's showing a shape difference rather than a size difference. Maybe something that's more familiar to you guys is oftentimes males tend to be larger than females. So sometimes we see size differences between the sexes. Males tend to have larger elements. So this is testing whether or not it's a size difference rather than a shape difference. So we're seeing shape differences, meaning it's likely ancestry. But for reliability, as I did not get the same results, it's likely that these equations are actually more applicable to a South African population rather than a North American one. But this opens up a lot of new questions. Why are there morphological differences in the spine? Is there a difference in development between these 2 ancestry groups? How do these measurements actually relate to the discriminant functions? We hope that it's testing that morphological shape, but again, it's sort of that black box model. And should these equations be population specific? maybe making new equations using my North American data would actually improve the classification of this method, but also begs the question of sort of differences between population groups and what that means as well. For now, metric methods based on the skull tend to be more accurate, and if you're going to use postcranial methods, probably going back to using four-disc, which I mentioned earlier in this presentation, is going to be better. But there should be a push to test and improve postcranial methods, because our validation studies show that Ancestry was causing the classification. So maybe we should be testing other areas of the skeleton to see, like how sex and ancestry interplay and what is causing classification and how it can help us as forensic anthropologists. Questions?
Questions for Rhiann?
Yes.
So I'm curious, because if you have intact skeletons, that likely means that you can get DNA. So how does this methodology compare to the accuracy and validity of DNA testing?
So DNA is always probably going to be the best, but it's very expensive, upwards of thousands of dollars to test DNA. Oftentimes, DNA will be used if we have an idea of who that individual is, but if we have no idea, we have to kind of fall back on these original methods. In addition, if there's anything like corrosion from chemicals or fire or something like that, we lose the ability to actually test for DNA. So these are just sort of methods, I guess, when DNA is not available. Yes?
So if you can do the measurements, if the cranium is present, if there's damage to it, can you kind of interpolate what that measurement is, or does it have to be fully intact? Like if it's chipped or,
Yeah, we tend to only use fully intact individuals. Oftentimes with the skull, because we have, I think, about 34 cranial measurements, if we're missing one or two, sometimes if the left eye orbit isn't available, we'll use the right or something like that. But if it's not available, we try not to use it rather than like putting something in, because with a measurement this small, a couple millimeters can make a big difference. Yes?
One more. So I'm curious, because you said that you took your specimens for your tests from the Cleveland Historical Museum, or so do you think that there's an effect of looking at older skeletons that are preserved versus looking at a modern population?
Yes.
Could you elaborate on that?
Yes. So I chose the historic population specifically because of those potential differences. So I wanted to use an older population. I wanted to test it to see if it would first work on this one, and if it does, then test it on a modern sample to see how actually applicable it is to a modern population. So it'd sort of be like a stepping stone in the process.
Other questions? Thank you.
Thank you.
Actually, I think that if anyone were going to be here, they'd be here, so we're going to go ahead. Our next and last speaker in this session is Andrea Ost, correct? And she's a student at Mercyhurst also. Age to death estimation from the auricular surface of the Ilium.
Thank you. Great, that's amazing. Okay, good morning, everyone. Thank you for coming. As was already said, my name is Andrea Ost, and I'm an instructor as well at Mercyhurst University. And today I'm happy to present to you about half of my thesis research from my master's thesis due to time constraints. And the title of my presentation is Age at Death Estimation from the Auricular Surface of the Ilium. And is it just the slide? Sorry, it's just this. Perfect, thank you so much. Okay, so it was already stated in the two previous presentations, a big part of what we do at Mercyhurst is forensic casework. So we do that for the states of New York, Pennsylvania, and Ohio typically. And so a large part of the role of a forensic anthropologist is in the creation of the biological profile. So, as was stated in the last presentation, the components of the biological profile are age, sex, ancestry, and stature. And so these are some different skeletal indicators that we can use in the body, our different regions of the skeleton, to estimate all of these parameters. So my research focused in age estimation. So there are really two different components to age at death estimation because there are two types of looking at age, or two ways of looking at age. So the first one would be chronological age, and that is your calendar days since birth. So that is really the minutes, seconds, hours exactly that you have been alive. And then there's what we actually see reflected in the skeleton. So that's age as it manifests in the skeleton is referred to as biological age. So we use what we can see in the skeleton, biological age, to attempt to estimate chronological age, but there is an imperfect correlation. But it's the best we have when we have only skeletonized remains. So when we're choosing skeletal indicators to be considered useful for predicting chronological age, there are three main requirements. So the first would be that there are unidirectional changes in that indicator. So the state, or the character state of an indicator, an area of the skeleton, only progresses in one direction and doesn't revert to previous states. The second requirement is that we're able to identify and classify these changes in the skeletal indicators both reliably and ideally across multiple populations, right? And the third is that these skeletal indicators are actually correlated with age. So there are two different ways to report this that we use for our case reports at Mercyhurst. And so the first would be point estimates. So this is just a chart showing different point estimates of multiple different age at death estimation methods, and then attempting to predict that chronological age. So a point estimate example would be like 50 years of age. But because that's very narrow, and because saying we think this individual is probably 50 isn't that useful to police investigations, we also report intervals. So we say, we think this individual, due to these methods that we've looked at, falls in the area between 40 and 55 years of age. And we'll sometimes even go a little bit broader than that, depending on what our different analyses have found. So we have point estimates, and then we have intervals as well. So when we're looking at skeletal indicators of age at death, the most common ones are cranial sutures. So looking at the closure of these sutures. Sternal rib ends, so looking at these areas down here at the ends of the rib that show increased osteophytic growth throughout life. The auricular surface, which is right here in the pelvis, and then the pubic symphysis, which is also in the pelvis. And my area of interest was focused in the auricular surface. So the auricular surface is the posterior medial portion of the ilium that articulates with the sacrum, so where your spine articulates with your pelvis, essentially. And so this is what the auricular surface looks like. So it's this area right here, so called because auricular means ear, and it looks a little bit like the shape of an ear. And we also see that the retroauricular area back here, so area behind the auricular surface, is useful in age at death estimation as well. So there are two scoring methods that we use to estimate age when we're looking at the auricular surface. The first is a phase method. So we would look at the entire morphology of this surface and see which stage the surface appears to fall into. And then we would use that character state, or that stage, to estimate age from that. But that doesn't take into account that potentially different things are changing at different times on this surface, especially since we have this area back here that can be sort of unrelated to this area, and both are useful in age at death estimation. So I advocate for a component method, which really allows you to treat each trait of the auricular surface or of your skeletal age indicator as independent. So what I looked at for my thesis was a component method that basically weighs all of these variables independently and then combines them at the end into an age at death estimate. So there are a couple problems with estimating age. The first being with the auricular surface, that although it is widely used, it's not a favored age at death estimation method. It's difficult to identify and score traits. It's not as accurate a lot of the times as other skeletal age indicators, and there are overall many improvements that can be made to the methodology surrounding it. Also, there are problems with age at death estimation in general. So the first one being that popular methods typically don't estimate age well over around 60 years. So we have these open-ended intervals. Typically you'll have a stage, if you're looking at different phase methods, a phase that would be 40 to 50, 50 to 60, and then 60 plus would be the highest category. So that's potentially neglecting about 40 years, potentially, of an individual's life. So that's the first problem, is that we need to be looking at indicators that are able to show these changes in older individuals as well, and help to provide more accurate estimates and precise estimates of age. And we also have broad age ranges. So a lot of age at death estimation methods will give you probably like 30, 40 year age ranges, which, while it is somewhat useful for narrowing down missing persons lists, if you have something like the cranial sutures that will typically give an age at death estimation of, let's say, like 27 years of age to like 88 years, that doesn't tell us a whole lot. That just tells us that at some point this individual was an adult and was alive. So it's not very useful in terms of an estimate that's that broad, or a range that's that broad for narrowing down missing persons reports. So that's something else that we need to get better at, and that we need continued research into. And the reason that we're seeing that really is that under about 30 years of age, your skeleton is still growing and developing. So after that around 30-year cutoff mark, though, we have increased variation, so that results in this trajectory effect. So really, you have your chronological age down here, your variation up here, and then this trajectory effect with as your age increases, variation increases as well. And it's very difficult for us to account for all those factors of variation, especially because a lot of that is associated with numerous factors that aren't related to age. So we have things like diet, health, nutrition, even like activity patterns. If you play sports more than another individual, that can wear down your bones in your joint cavities more, and so your skeleton can look older than you actually are. So all of that is things that, that we can't necessarily account for just from skeletonized remains. So this is an increasing problem. So there are some methods that have attempted to account for these shortcomings. Transition analysis is one of them, and that's what I did my thesis research on, or half of my thesis research on. And transition analysis specifically was interesting to me because it claimed to more accurately estimate the age of individuals in those upper age classes, so around 60 plus years of age, when before we aren't seeing precision or accuracy in those ranges. So what my research was really aiming to do was to understand the different traits that are associated with the auricular surface, how those are distributed throughout the lifespan. So if we see a higher frequency of traits in the lower age classes rather than the upper age classes, and then the reason for that. And so looking at the trait distribution and presence throughout the lifespan by analyzing a component method. So again, component method, treating all of those traits as independent of one another. And so that would be transition analysis. So to do that, I asked two questions. The first being, which traits are actually most useful for accurately estimating chronological age of death? And the second being, is the auricular surface itself actually useful for estimating age of death? Because if it's not useful, especially in those upper age categories, and if people don't like using it, I would argue that maybe we should stop using it. So transition analysis uses Bayesian statistics to combine multiple skeletal age indicators, so the cranial sutures, the pubic symphysis, and the auricular surface. And this is interesting because it can be performed with fragmentary remains. So this is very useful for us in the field because sometimes we'll have damage to one or all of these areas, particularly from things like postmortem damage, so even someone accidentally stepping on the remains, or things like carnivores and scavengers will damage the remains as well. So this is very useful if it works. So it basically works by scoring each of these different age indicators and then entering those scores into this computer program at Boo. And that results in a maximum likelihood estimate, so that point estimate of, let's say, like 55 years, and then also in 90 and 95% prediction intervals, so giving you an interval range as well. And this is what the program looks like. So transition analysis uses 9 traits. I won't go into them all. That may get boring for you guys and too technical. But I will show you the differences between a young auricular surface and one of an older individual, and sort of what transition analysis looks at with these different traits. Are these changes from the younger one to the older one? So we can see that if we were scoring these auricular surfaces due to our using the criteria for transition analysis, if we're looking at these different aspects, the characteristics are undulating, median elevation, and flat to irregular. So this one shows an undulation. You see these nice striations here, and you see that the surface itself flows nicely. And then this one would be flat to irregular, because this is an older individual who's had osteophytic growth, or bony deposits, laid down on this auricular surface over life. So from my research, I used a sample from, again, the Hem&Taw collection at the Cleveland Museum of Natural History. And that's actually the largest modern documented human skeletal collection in the world. So it's pretty ideal because of A, its proximity to Erie, and B, because of that sample, although it is historic. So I used 400 individuals, and their age ranges were from 16 to 93 years. And I started at 16 because we have very different age at death estimation methods for juveniles. So I wanted to start at the teenage years and then up to 93. So this sample was balanced as evenly as I could between the ages, sexes, and ancestries of all of these individuals. So you can see here, I tried to balance it based on what the collection had available between white and black males and females for a total of 400 individuals. So I scored each individual, or each pelvis, using transition analysis. And important to note about this is that I entered the auricular surface into that computer program in isolation, and I didn't use the other 2 skeletal indicators that transition analysis uses. So if you remember, it uses the pubic symphysis as well in the pelvis, and then also the cranial sutures. So for the purposes of my research, I just looked at this one skeletal indicator, which is not necessarily how the method is meant to be used, but it was best for this research. To assess the correlation with age, I used Spearman's rank order correlations for both the individual traits, so those 9 traits on the auricular surface, and the total method scores as well. So how closely correlated with age, those actual point estimates, and then the intervals, that 90 and 95% prediction interval was correlated with age. And to do this, I used past paleontological statistics software package. Okay, so these are my results for the traits. So you can see the 9 traits here. We've got the p-values on this side just to show that all of the traits are correlated with age. So that's a good first step. And then we have the R value here, which is the strength of the correlation. So the highest correlated trait was superior demi-face topography in the auricular surface, and that R value is 0.62. On a scale from 0 to 1, that might not look that good, but we're looking at Spearman's and not Pearson's correlation, so this is actually better than it looks for Spearman's. This is fairly highly correlated. Then when we're actually looking at the method scores, so we have this one trait that's accounting for quite a bit of variation in the auricular surface, around 38%. And then when we're looking at how the method scores themselves performed, when I looked at those point estimates, so just the simply, I think this individual, due to this computer program's readout, is 55 years old, I found that 87.5% of the time, the documented ages, are those actual chronological ages of the individuals, were actually within the age ranges that were provided by the computer program associated with the method. So 87.5%, again, might not sound that good, but given that this is only one skeletal indicator and the method is supposed to use all 3, this is actually pretty good news for the auricular surface. So here's a plot of those documented ages, are actual chronological ages, against the estimated ages, and these are the point values, or point estimates. So here's the line of best fit going through the center, and how would it compare to the identity line if the method was performing basically to the best of its ability or perfectly? So that's the identity line. So you can see that the slopes aren't actually all that different, but we are getting a very interesting distribution at this end and this end. So we have this rather disparate distribution in what looks like the middle age categories, where the method is not working very well in this area. And we see down here these points pulling towards the this area, which is good news, but expected, right? Because it's easier to estimate the age of younger individuals because a lot of that variation hasn't set in yet. But we see the same thing reflected in the upper age regions. So basically the same phenomena happening in both the lower and upper age classes. And this is, in the upper age class, pretty unprecedented because, again, we don't have accurate age of death estimations methods for older individuals. So this is really surprising when I saw it. And then, of course, we have that disparate range in the middle as well. So looking at the results of transition analysis, I split up these age classes into young, so around 16 to 34, middle to around 35 to 59, and then old 60 plus. And that's just based on what's in the literature already, so building on the literature for finding these categories. And then looking at the average inaccuracies of this method, we can see that with the young, in years, it's 9.04 years is the average inaccuracy, and then in the older individuals, 10.28 years is the average inaccuracy. So that's not highly accurate necessarily, but when we're looking at those intervals that are provided by the program as well, remember that 87.5% of the time, those individuals are still falling into those intervals, which is good news. But these are a lot more similar than they have been in any other method that's been presented so far, so that's very interesting. And then again, that middle area has a lot more disparate distribution to it. So in conclusion, first off, that question that I asked, is the auricular surface actually useful for age of death estimation in the older age categories? Well, with transition analysis, yes, it is. It performs pretty well in both the upper and lower age categories, and all 9 traits are correlated with age. So my thinking is that when we combine all 3 skeletal indicators used by this method instead of just using 1, we would see much higher accuracy rates in those middle age ranges, particularly because some of those other skeletal indicators show these really nice documentable changes in the middle age ranges, but they, again, haven't seemed to show them in the upper age ranges. So if the auricular surface can provide us those changes in the upper age ranges, working in tandem with those other skeletal indicators could provide a lot more accurate and precise results for estimating age of death. So I do argue that we should be using it, and that we should continue research into particularly finding traits and identifying traits that can accurately and precisely estimate age of death in those older age categories. So here are my references. And does anyone have any questions?
Question for Andrea?
Yes.
When you show the skeleton, you show like 3 highlighted areas that you look at. And it seemed with the other 2 presentations, closer to the head, you're getting more information. Like, is there anything from the legs down to the feet, like any information that is ever gathered there, or is it just
That's a very good question. A lot of the time when we're looking at age of death estimation, we're looking at joint surfaces that are hopefully less mobile, so it's not as affected by the movement of the body and then the wearing down of that cartilage over time. So we're hopefully finding things that are less mobile joint surfaces, and a lot of the time that's in places like the pelvis, just where that spine and the pelvis meet together, because in the head we have a lot of rotational movement, and then in the limbs as well we have a lot of movement. So the pelvis is really one of the most useful, probably the most useful indicator for age of death, just because of that reason. But there are other methods that have tried to estimate age using pretty much everything. So looking at even, the growth on the kneecap and how well is that correlated with age. So a lot of things have been tried, but the best thing is probably the pelvis. Any other questions? Okay. Thank you.
session is lunch, and that goes, we'll be back in this room at 1:20, so from 12:20 to 1:20, enjoy yourselves. And lunch, of course, is in the Sunset Cafe.